Section 5.6, complex numbers. Complex numbers are made up of imaginary numbers. In math, we represent imaginary numbers with the symbol I. The imaginary number I is the principal square root of a -1. In other words, I equals the square root of a -1. And when I simplify radicals, in place of the square root of a -1, I can put I. Imaginary number is a number in any form of a plus bi, where b can't equal 0. If b was 0, my imaginary part would drop out, and I'd be left with my real part, a constant. I, as stated below, is the square root of a -1. A number with the form of bi is a pure imaginary number. That's why if this was 0, that would drop out, and I'd be left with a real number. Our first set of examples, they want us to simplify each number by using the imaginary number I. Here I have the square root of a -9. I know that imaginary number is I equals the square root of a -1. So what I have to do is to break a -9 into a product of factors, 1 being a -1. Therefore, 9 times a -1. I know the square root of 9 is 3. And from the previous slide, I know the square root of a -1 can be represented with I. Therefore, when I simplify, this is 3i. 2 square roots of a -16. Again, I can break this into a product of its factors. 16 times a -1. I know the square root of 16 is 4. 4 times 2 is 8. Square roots of a -1, but I know the square root of a -1 is I. Therefore, 8i. Here I have the square root of a -20. That can break up into a product of its factors, 1 being a perfect square, 1 not a perfect square, and also a -1. So I have 4 times 5. 4 is my perfect square, and also times a -1. And when I multiply these together, I get a -20. But I know the square root of 4 is 2. The square root of a -1 is I. And that leaves me with a 5 in the radical. So I have, when I simplify, 2i square roots of 5. On my next example, a -4 square roots of a -54. I bring down my -4, my radical, and again, I can break this into a product of its factors, 1 being a perfect square. That would give me 9 times 6, which is 54, times a -1. The square root of 9 is 3. 3 times a -4 is a -12. The square root of a -1 can be represented with I, and that leaves me with 6 in the radical, a -12i square roots of 6. Here I have a -5, and I break this into a product of its factors. 121 is already a perfect square, so I have 121 times a -1. The square root of 121 is 11. 11 times a -5 is a -55. And the square root of a -1 is I, a -55i. 3 times the square root of a -48. A -48 can be broken into a product of its factors, 1 being a perfect square. The biggest one is 16. And that would be times 3. And to make that a negative, times a -1. The square root of 16 is 4. 4 times 3 is 12. The square root of a -1 is I, times the square root of 3. 12i square roots of 3. On previous slides, we've seen a plus bi. Here we're going to define that as a complex number. Imaginary numbers and real numbers together make up the set of complex numbers. A complex number can be written in the form of a plus bi, where a and b are real numbers, including 0, and I is equal to a -1. So when I have a plus bi, I have a real part, which is represented with a, and b is also real, but when it multiplies times an imaginary number, it becomes the imaginary part of my complex number. But if b is 0, then this would drop out and just leave me with a real number. In our first example, we want to write each in the form of a plus bi, and it has to be in that form, my real part and my imaginary part. If it's not in that form, then I have to rearrange that. Here, this is in that form. I have my real part, 3, minus the square root of a negative 36. So it's in the form of a plus bi. All I have to do is simplify. 3 minus the square root of. Then I'll just break this into the product of its factors. 36 times a negative 1. Bring down my real part, 3 minus the square root of 36 is 6. The square root of a negative 1 is I. 3 minus 6i. Here I have the square root of a negative 7 minus 5. It's not in that order, so I can rearrange it. My 5 is negative. My square root of a negative 7 is positive. And I'll break this into the product of its factors. 7 times a negative 1. Bring down my negative 5 plus the square root of a negative 1 is I. And 7 still in my radical. A negative 5 plus I square roots of 7. Again, this isn't in the correct order, so I'll rearrange it. My 10 is positive, plus the square root is positive, and I'll break this into the product of its factors. 4 times 11 times a negative 1. I bring down my 10. The square root of 4 is 2. The square root of a negative 1 is I. And I have the square root of 11 staying in the radical. So 10 plus 2i square roots of 11. Here we have a diagram of the complex numbers. We know that it's made up of its subsets, imaginary numbers, bi, and its real numbers, a. The real numbers are broken into its subsets of rational numbers and irrational numbers. And inside our rational numbers, we have its subsets of natural, whole, and integers. In previous sections, we have graphed ordered pairs on a real number coordinate plane. We have an x value and a y value. Therefore, we have an x-axis and a y-axis. But if we want to graph a complex number, we need to graph that on a complex number plane. Here, you can use the complex number plane to represent a complex number geometrically. We locate the real number part of the number on the horizontal axis and the imaginary part on the vertical axis. As you can see on the real axis, we have the origin at 0. To the right are my positive reals. To the left are my negative reals. On my imaginary axis, I start at the origin 0. Above are my positive imaginary numbers, and below are my negative imaginary numbers. With a real number coordinate plane, I use a ordered pair, x and a y, and I graph that in reference to my x and y axis. Here, I graph a complex number, the real part a, and the imaginary part bi. Here we want to graph the following complex numbers on this complex number plane. My first one is a negative 2 plus the square root of negative 9. I first need to simplify this into my complex number form. Negative 2 plus the square root of 9 is 3. The square root of a negative 1 is I. Now I can graph. My real part is a negative 2. And my imaginary part is positive, so it's 1, 2, 3. A negative 2 plus 3i. Next, I want to graph 4 minus 2i. So a positive 4, 1, 2, 3, 4, and down 1, 2i. 4 minus 2i. My next one is a negative 6 minus 5i. 1, 2, 3, 4, 5, 6, and a negative 5i. 1, 2, 3, 4, 5. And my last one, 5 plus the square root of a negative 49. Again, I need to put this in complex number form. 5 plus the square root of 49 is 7. The square root of a negative 1 is I. And when I plot that, that'll be a positive 5. 1, 2, 3, 4, 5. And up 7. 1, 2, 3, 4, 5, 6, 7. On this example, they want me to name the complex numbers represented by each point in the graph. Let's begin with this one. Here I'm going to have 1, 2, 3, 4, 5, 6, 7, 8. A negative 8 plus 2 I. The next one, I have a negative 1, 2, 3, 1, 2, 3, 4, 5, a negative 3 minus 5i. For my next point, I stay on the origin, which is 0 for my real part, and it's going to be 1, 2, 3, 4 plus 4i. My next point, 1, 2, 3, 4, 5, and this would be plus 0i. My next one, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. This would be 5 minus 7i. And my last point, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4. 9 plus 4i. If we take a look at this point, 0 plus 4i, it's perfectly acceptable to write this as just 4i. And the same with this point. I have 5 plus 0i. It's perfectly acceptable to write this as just 5, because we can identify that this is an imaginary part and there's no real part, and here would be a real part with no imaginary part. I feel just writing it this way helps clarify the situation. In a complex number plane, there are times we want to determine how far a complex number is from the origin. To do that, we have to find the absolute value of the complex number. That's going to be the distance from the origin on the complex number plane. So, our general rule is we want the absolute value of the complex number. We know the A is the real part, B is part of the imaginary part, but it is a number associated with my imaginary number. To determine the absolute value, we're going to use the square root of A squared plus B squared. We know we can determine A, and we know we can determine B. All we're going to do is substitute in and calculate the distance. Here they want me to find the absolute value of each complex number. Here is the absolute value of a negative 3i. If we wrote this in complete complex number standard form, that would be 0 minus 3i. And A would equal 0, B would equal a negative 3. And I would use the square root of A squared plus B squared. Substituting in, I'd get 0 plus a negative 3 squared. And this would be the square root of 9, and my solution would be 3. Here I have the absolute value of 4 minus 5a. A equals 4. B is equal to a negative 5. I substitute into a squared plus b squared. A squared is going to be 4 squared plus a negative 5 squared. That gives me the square root of 16 plus 25. And when I simplify, I get the square root of 41. And this is in simplest form.